In this video tutorial, we will look at how we can train the YOLO11 object detection model on a custom dataset. We will train the YOLO11 object detection model on a personal protective equipment dataset, which is available on Roboflow. So here is a quick demo of how our results will look like at the end after we train the YOLO11 object detection model on personal protective equipment dataset. So over here, you can see that we are able to detect the protective helmet, protective boots, safety vest. Along with this, we will also be able to detect the gloves and the eyewear as well. So this is a quick demo at how our results will look like at the end. So let's move towards the coding part. So over here, you can see that we have created a Google Colab notebook. So I have written all the code already. So you can see over here, we have written all the code. I have done the training as well. And you can see we have some results over here as well. And then we will test the fine-tune model on random images as well as on videos as well. Okay, so we will cover all this in this video tutorial. So let's get started with this. So before we run the script, please make sure that you have selected the runtime as T4 GPU. Yes. Okay. And now you can see we have the T4 GPU available over here. So Google Colab offers free GPU. Like you can see over here, like it can last around 1 hour, 20 minutes, which is enough for this task. And we have a GPU RAM of 15 GB available over here and system RAM of 12.7 GB, which is enough for this tutorial and project. Okay. So let's first run this. So this will tell me that if I am using the GPU memory or not. So currently I'm using the GPU memory. Okay, but no process is running because I'm not training the YOLO11 model currently. Then we need to install the ultralytics package. Okay. So over here, you can see we are installing the ultralytics package. So this will take some time. Okay, so now it's done. So you can just hide the output so your notebook looks more clean. So now we will check that if we have ultralytics working fine. So now you can see over here, ultralytics 8.3.1 version is currently running over here. We have Python 3.10 available and we have CUDA available test at T4 GPU. And we have 2 CPU cores available of 12.7 GB RAM. Okay, so that looks fine. So we are using ultralytics with version 8.3.1. Okay, so now from ultralytics, I will import YOLO. So when you import YOLO, you can just call any YOLO model. You can call YOLO 8 model over here as well. You can call YOLO 11 model over there as well. So now to display any input or output image in the Google Colab notebook, we will import the image library from ipython.display. Then I will be downloading the dataset from Roboflow. So let me just show you this dataset over here as well. So we will be using this dataset, which is available on Roboflow over here. Okay. So in order to use this dataset to fine tune your YOLO V11 model, you just need to log in over here on Roboflow. So you can just click over here and you can sign in with Google with your GitHub account or with any other email like Yahoo email as well. So I will just sign in with my uh, Google account over here as well. Okay. So now you can see over here, we will use the version 2 over here. And you can see here is our data set. We have around 3,290 images available over here. And we have around 2,311 images in our train set, 652 images in our validation set, and 327 images in our test set. So we have our data set split as like we are using 70% of the data for the training purpose, 20% of the data for the validation purpose, and 10% of the data is used for the test purpose as well. Okay. So this is how our data set looks like. Okay, so now I will just download the dataset. In order to download this dataset, you can just click over here. Then you can select the YOLO V8 format because, okay, you can either select the YOLO V8 or YOLO 11 format. Okay, and then you can click on show download code. Over here. And then you can just copy this code from here and just add this code over here. Okay. So now this will download the dataset. If you run the cell over here, it will download this dataset into Roboflow. And now you can see that dataset is being started to download. So this will take some time. So now it's around done. Okay, that looks good. So now we have downloaded the dataset over here. Okay, so we have the train test validation dataset. So here is our data.yml file. So over here, you can see that we have a number of classes as 7. So we have total 7 classes. We have the dust mask class, IVR class, glove, protective boots, protective helmet, safety vest, and shield task. Okay. So these are the different classes that we have in our data set over here. Okay. So one thing you can do first before you go ahead is here is our train test images and validation. So you can just copy path from here, okay, and just update this path first, okay, and then you can just click over here, copy the path, and just update this paths over here, and then you can just click over here, copy path, and just update this path over here. Okay. So here is the link of the dataset as well. You can just view this dataset by copying this link and adding this into another tab over here as well. Okay, so that looks good. Okay. So now if I just write over here, basically our dataset is being saved into the variable dataset. And if I just write over here dataset.location, this will tell me the location of the dataset over here. Okay, so now we will train the YOLO11 model on a custom data set. So you just need to add the model over here. Okay, so if you are currently we are using YOLO11 model, so you just need to write YOLO11. We are using YOLO11 medium model, so you just need to write YOLO11 medium model, and we will be training or fine tuning the YOLO11 model on, like, we can say that 50 epochs, because this will be enough. Okay, and toss is equal to detect, mod is equal to train, and I'm just passing the location of the data.yml file over here. Okay, and the default image size, basically our YOLO11 model is being YOLO11 model is being trained on the image size of 640 cross 640. So it's better if we fine tune the YOLO11 model on the same size. So plus we can like fine tune it for 40 epochs, like that will be fine as well. So let's run this. So I'm just showing you like how you can train the YOLO11 model. Now you can see it's downloading the my dataset model over here as well. Okay. So now you can see that the training has started. So let's wait for the training to get complete, or I will just show you after it completes 10 epochs or so. Okay, so let's wait for it to get complete. So you can see that training is still in progress. Currently, 30 epochs are being processed out of 40. And if we just see over here, I made one change. Previously, I was using YOLO11 medium model, but now I'm using a YOLO11 nano model, which is the smallest in size, and it is the fastest, but it is least accurate among the YOLO11 models. The reason is that because to process an epoch, the YOLO11 medium model was taking around 3.5 minutes. So it will take consume a lot of time. So I just shifted to YOLO11 nano model, which is taking around 53 seconds to process an epoch. Okay, and currently 31 epochs are being processed. So let me try to explain you a few things in the meanwhile. So now over here, you can see that we are using YOLO11. We can just close the dataset tab. We are using, these are the different parameters. We are using the YOLO11 nano model, and we are using we are just training or fine tuning our YOLO11 nano model on this personal protective equipment data set. We have set the epochs to 40. The patience is being set to 100. Like if we are getting the mean average precision, like this is the mean average precision with IOU threshold intersection our union threshold as 50 or 0.5 is 0.421, and mean average precision when IOU threshold intersection our union threshold varies from 0.5 to 0.95 is 0.238. So the patient's value is being set to 100. So if the mean average precision remains same for 100 epochs, then we will stop the training. Okay, so this is what patient value reflect. Then we have batch size is equal to 16. Like in each batch, we will pass 16 images to our model. Okay, so for training, in each batch, we'll pass 16 images to our model for training. So what does this mean? So these are the number of batches. 142 are the number of batches. Okay, so in each epoch, we pass 142 batches. Okay, so like you can see over here, and in each batch, we have 16 images. So if I just show you over here, number of images. So we have 2271 images in the training. Okay, like you can see over here, we have around 22,271 images in the training. You can see over here. Okay, so what we can do for here is if you divide this number with 16. Okay, so now let me just, if I just open the calculator from here. So as I told you that in each batch, we are passing 16 images. So if you divide 2271 divided by 16. So like you can see over here, these are the number of batches. So but we have 142. And if I just show you over here, like you can see over here, we have 142 batches as well. Okay. And over here in the validation, we have around, in the validation, we have around 637 images, like you can see over here. Okay. So if I just divide 637 divided by 16 is equal to around 40. But you might notice over here one thing, that we are the number of batches should be 40, but the number of batches over here are 20 because we have reduced the size of the batches. So you can say that we are just passing 32 images in each of the batch over here in the validation. Okay. So, and if you just go over here, we are setting, we are just fine tuning our YOLO11 model by setting using the default image size. Basically, YOLO11 model is being trained on the by using the image, setting the image size of 640 cross 640, like 640 is the width and 640 is the height. And we are just fine tuning the YOLO11 model by setting the same image size of 640 cross 640. So if our image are larger than 640 cross 640, then it will be compressed to 640 cross 640. So it is better if you don't change the values of the image size and keep it default, because if you just vary those values, like if you increase the image size or decrease the image size, the performance of the model might get compromised as well. Okay. So we have the batch size 16, and and in the train 3 folder, our results will be saved. Okay, so if I just go to run detect, so in the train 3 folder, we have our weights and everything. Okay, so we are using the pre-trained model, so it's true. We are using the optimizer automatically defined. Okay, verbose is equal to 2 because you can see we are just getting the detail, like after each epoch, the mean average precision we are getting. So we are just getting all these details. So this is because we have set the, by default, the verbose is being set to true. Okay. And if we just go ahead, okay. So, and then we have, uh, So these are all the other parameters. You can just change pass these values parameters over here. These are the by default set values. Uh, I was just trying to show you one thing, the maximum number of detections. Okay, so you can see that the maximum number of detections are being set to 300. So it will detect maximum 300 objects in a frame or in an image. Okay, and this is the non-mix suppression intersection over union value is being set to 0.7. Okay, so so basically, non-expression is a technique that is used to remove redundant or overlapping bounding boxes. Um, so all the objects that have an intersection over union, like uh, below 0.7, are being removed or treated as false positive. Okay. Okay, so if the intersection over union of the two bonding boxes is below 0.7, then the bonding boxes which have a low confidence threshold will be suppressed. So this is what we mean by IU over here. So, and then all these are all the other parameters. So this is what we need to know. So let's see where our training has progressed for now. So we are done with the 37 epochs. Okay, so this will take around 2 minutes more. So let's wait for this to finish. And you can see over here, we are just getting mean average precision with intersection over union threshold as 0.5 or 50% is 89.8%. And the mean average precision with intersection over union threshold varies from 50 to 95 or 0.5 to 0.95 is 0.617 or 61.7%. So these are all the calculations that are obtained on the validation set. So basically, we are not using the validation images like we have 637 images in the validation. So we are not using the validation images for the training. So these are all the mean average precision scores on the validation data set. Okay. So, so as we are not training our model on the validation data set, so we can just use the scores and see how our model perform. Okay. So basically, the mean average precision score on the validation dataset tell us how better our model generalizes. Okay. So now you can see that training is being done, and you can see that we are just getting the mean average precision scores for all the classes. These are the scores that are obtained on the validation dataset, and our best model are saved into this train tree. And best.pt. So these are our best model weights. Over here we have, okay. So now you can see that the mean average precision score for only shield class is low, like it's 0.763, and mean average precision when IOU varies from 50 to 95 is 0.467. Else, for all the classes, it's much high. Okay, and the precision and recall scores are also a bit low. Okay. The reason might be that for the shield class, we don't have very much data available, like for in the training as well as in the validation. Like you can see over here, we have in the validation, we have 637 images and we have only 25 images for the shield class. Similarly, in the training, we have also very low data for the shield class as well. Like if we increase the data, might be we might get better results. Okay. So now if I just go to over here, we have the precision curve, recall curve, the confusion matrix. So let me just show you the precision curve first over here. So one thing you might notice that as the confidence value increases, now you can see what is precision first. Uh, Precision is basically number of true positives, like how much correct predictions we got out of all positive predictions, like true positives divided by true positive plus false positives. So in short, you can say that precision is the number of correct predictions like we got. Okay. So now you can see that as we increase the confidence threshold, the precision value continues to increase. Okay. Now you can see that as we increase the, now you can see we have the, for each class, we are just getting a separate precision curve, okay? And as we increase the confidence threshold, the precision value is increasing, like you can clearly see over here for all the generally for all the classes. So this means that at a higher confidence threshold, the model is making very low false positive predictions. As we increase the confidence score, the model became more certain. And although it might make very less predictions, but it will make correct predictions. Okay. So as we increase the confidence threshold, the model makes very less false positive predictions. We can clearly see over here. While we can see that when we have a low confidence score like 0.0, we have a very low precision score. This is because we are just getting many false positives in our predictions. When we get more false positives in our prediction, our precision value drops. And when we get no false positives, like when we increase the confidence score, we definitely don't get very much false positive. So our precision increases. So this is how it relates. And you can see over here, this fluid curve is for all classes. And we can see over here at 0.959 confidence threshold, we are getting a precision score of 1.00. So this means at 0.959 confidence threshold, we are getting a precision score of 1.00. And here we have the recall confidence curve over here. So we can see that the recall value for all the classes drops as we increase the confidence scores. Like you can see at low confidence, we have at low confidence score, the recall value is high. And as we increase the confidence score, the recall value drops. So basically, recall tell us the true positives out of all ground truths. Okay. So what does this mean? Like when we have a low confidence score, like in recall, we are not worried about false positives. Okay. Only in recall, we are worried about the true positives. So when we have a low confidence score like 0.0, we are getting more predictions. And in generally, when we have more predictions, we might have very much high false positives, but we also have many true positives in our predictions as well. So in recall, we are only concerned with the number of true positives. Okay. So as we decrease the confidence score, we might get a lot of true positives. So we have a high recall at low confidence. And when we increase the confidence score like 1.00, we might not get very much predictions, like the prediction rate drop. Like if we have the confidence score 0.0, we are getting, for example, 10 predictions. And when we make the confidence score 1.0, we might be getting around 1 or 2 predictions. So when the prediction rate drops, so it might mean, you can say that we might get less true positives. Okay. So therefore, the recall score also drop because we are getting less true positives. So because when we increase the confidence score like 1.0 or 0.8, there will be less detections, okay? Because it will only keep the draw bounding boxes around those detected objects which have a higher confidence above 0.8. So definitely the predictions will drop, and we might have, although we might get low false positives, but we are also getting very much low true positives as well. So therefore, our recall score will drop. But one benefit is that when you increase the confidence score, you might get fewer predictions, but they will be more accurate predictions. So remember this, when you increase the confidence score, you might get fewer predictions, but they will be more accurate predictions. Okay. So this is the confidence score. So the confidence score basically tells us how our models handles different classes. So for example, for a dust mask class, like you can see that at 292 times, our model detected correctly that there is a dust mask, while 16 times when there is a dust mask, our model was unable to detect, like our model detected nothing. And 128 times when when the user was wearing an eye wear, our model detected correctly that the person is wearing an eye wear, while one time when the person was wearing an eye wear, our model detected it as a shield. And 18 times when the person was wearing an eyewear, our model detected nothing. Okay. Similarly, 725 times when the person was wearing protective helmet, our model detected correctly that the person is wearing protective helmet. And 23 times when the person is wearing protective helmet, our model is unable to detect anything. Okay, and one time when the person is wearing protective helmet, our model detected as safe shield. And two times when the person is wearing protective helmet, our model detected as safety vest. So confidence metrics tell us how our model handles different classes. Okay, so you can just run these. There will not be very much difference. Okay, okay, that's fine. So now over here, now using these are the normalized confusion metrics. Okay, so now you can see 93% of the times our model correctly detected correctly that there is a dust mask, while 7% of the time our model detected incorrectly or our model was unable to detect anything. 80% of the time our model detected correctly that there is an IVR, and 1% of the time when there is an IVR, our model detected it as a shield. So this is how we can use confusion metrics. Okay, and then this tells us how much data we have in our data set. Like you can see over here, for the shield class, we have very much low data, like very less data. For the IVR, we also have less data, but for the uh, protective boots, protective helmet, safety vest, we have huge amount of data. Like these, we have 2000 instances around for the glove. Okay. So now you can see these are the results over here. Now we can see that the mean average precision is increasing. We have loss decreasing. So this is how. These are the model predictions on the training batches. Okay. And these are the model predictions for the validation batch. And this looks good. Like model is able to detect protective boots, gloves. So we have not used the validation data for the training. So it's always better to take a look and see how our model is performing. Okay. So now what I can do over here is these are my model weights. So one thing I can do over here is I will just save this model weights into the drive. So now what I will do is I will just write. I just need a code to mount Google Drive with the Google Colab. Uh, yes, that yeah. So I can just do is I can just copy this from here and I can just run this over here. I will just connect to the Google Drive now. Okay. So this will take a second. In the meanwhile, I will just open a drive over here. So this is my drive. Okay, so if I just refresh this, we have the drive over here. Okay. Okay, so one thing I can do is I will just write move, and I want to move these weights. Okay, from there to in which folder I want to move this. I can just move to this. Okay, so let's see. And now if I just go to YOLO7 over here, I should have best one. Yeah, where we have our weights. So one thing I can do over here is, so you can just copy this link from here. Oh, we only need this link, like you can share. Uh, so what we can do is you can just delete this cell. So let's see if it works on. So now you can see we are able to download the model weights, and you can see we have our best model weights over here. Okay. So now we'll just pass those best model weights, and we will now validate our fine-tuned model. So we'll see how our model generalizes. Okay. So, so now you can see over here we have 637 images, and we are just passing those images in a batch of 16. Okay. And so we have total number of batches as 40. And you can see over here, only for the shield class, we are just getting a bit low mean average precision. Else for all the classes, we are getting good precision, recall, and mean average precision score. Okay, and our results are saved in over here. Okay, so we have the confusion matrix, F1 curves, all those. So now we will just test our model or perform inference or with our fine-tuned model on the test dataset images. Okay. So just in that we have these images, and we are just trying to perform inference on this test dataset images. So we have around 322 images in our test dataset. Okay, so it will take a few seconds. So now I will not display all these images over here. I will just try to display like 3 images over here. And let's see how our results look like. Basically, this is the unseen data. We have not trained our model on a test data set. So our model is able to detect glove, dust mask, helmet, safety vest, glove, protective boots. Results look good. Dust mask, glove. So now you can see that our results look quite promising over here. Okay. And now I will just download a sample image from a drive and see how our model performs. Okay, so I'm just setting a confidence threshold of 0.25, and I want to save the results. And let me just display these results over here. So now you can see we are able to take the safety vest, protective boots, safety vest, protective helmet. Like we are just getting good results. So now I will download 2 videos from a drive directly into this Google Colab notebook so that I can test this fine-tune model. Okay. Okay, so in the meanwhile, let's run this up as well. So now the complete video is being divided into 310 frames, and we are doing detection on each of the frame one by one. And in the output, we have a complete video. Okay, so let me just display this output video over here. So this will take a few seconds before we have the output video being displayed over here. Okay, but you can see our output video is basically saved over here. This is our output. Now you can see the size is 92 MB around. So it will just compress the size, like you can see over here, it's around 3.7 MB. And now we will display this output video over here in Google Colab Notebook. So this will take some time more, and where we have the output. So here is our output video in the Google Colab Notebook. And let me download this video and show you how our results look like. Okay. Now you can see over here, we are able to detect the safety vest, protective boot, protective helmet. The results look quite very promising. Like you can see over here, we are able to detect safety vest, protective helmet, protective boots. Okay, these results look quite promising to me, like very good results. Like you can clearly see over here. Uh, In the same way, we can test our model on this other video over here as well. So now you can see the complete video is divided into 267 frames, and we are doing detection on each of the frame one by one. I'm just saving down the notebook. Okay, so let's run this over here. Mhm. Okay, so now we are just our output video is being saved to over here, detect, predict for, and I'm just trying to display the output video over here. This Google Colab notebook. So this will take few seconds. So in short, in this tutorial, we have learned that how we can fine tune or train the YOLO11 model on the personal protective equipment data set. You can also train or fine tune the YOLO11 model on any other data set as well. And our results look quite promising. You can clearly see it. So this will take few seconds before we have the output over here. So here is our output video. Let me download this video and just open this video now. So over here, you can see that we are able to detect the safety vest, protective boots, helmet protective. So our results look quite good. In this tutorial, we have seen that how we can train or fine tune the YOLO11 model on any custom data set. That is all from this tutorial. Thank you for watching.